So, all right, class. So we are looking at this example in section 10.5, which you already have copied down. And this is an example that I think will be helpful for the homework. So again, what we're dealing with here, what we have here is we have a sphere centered at the origin of radius 10, and then we have the top half of a cone. Okay, because remember, if you square both sides of z equals square root of x squared plus y squared, you'll get z squared equals x squared plus y squared. And we can put like ones underneath each of those. And so that fits the form of a cone. If you look back at section 9.6, table 2, a cone, this format here, z squared equals x squared plus y squared, is a cone. And we recognize a cone as something that looks like this. It's a standard cone, passes through the origin. Okay, so it goes above and below the origin. But because we were given this equation here, z equals the positive square root of x squared plus y squared, the portion of the cone that we're looking at is just the top half of the cone, the top part. And so what we have here is we have a cone emanating from the origin that goes up until it hits the sphere of radius 10. And what that is going to look like then is what I have drawn here in this picture. So the surface S is the portion of the sphere, I want to say it the right way, it's the portion of the sphere, the surface is the part of the sphere that lies above the cone. So what happens, right? What happens is the cone, I mean, if we were to, draw a little more of the cone, okay, I mean, the cone keeps going, right? It keeps going. But we want the part of the sphere that lies above the cone, and that's the shaded part here. Now, the vector function, a vector function, or a vector of two parameters that traces out this shaded area, S. Okay, well, we need to discover what that vector function is. In other words, we are wondering, what is this vector function? What is it? Okay, so it's helpful to be able to find that. So how are we going to find that? Now hold on here. This is not shaded everywhere it needs to be shaded. I mean, it's not. There we go. That's better. Okay, so, well, one thing that we notice is the surface S doesn't go on forever. Okay, it doesn't go on forever. So that means if we're going to let our parameters, be parameters X and Y, they're going to have to be some restrictions on those parameters. Okay, because well, there just has to be, right? So what is important is to find the intersection between the cone and the sphere, because that intersection is going to form this rim here that bounds the surface, and based on that rim, we can get the domain for our parameters X and Y. So for the intersection, what we do is we set the equation of the sphere equal to the equation of the top part of the cone, and we're going to solve that. And when we solve that, we end up getting that 50 equals x squared plus y squared. So basically, you're trying to figure out along that rim, that green rim there, that's the intersection of the sphere and the cone. What's the restriction on the parameters x and y? X and y are the xy coordinates of the points that are on that rim, that intersection. So we set the spherical equation equal to the cone equation, and when we do that, and I'm trying to make sure everything shows nicely here. When we do that, we end up getting that 50 equals x squared plus y squared. And so this means that the x and y values that satisfy the intersection equation are coordinates of points where the points are, well, yeah. So I want to say this the way I have it written. I have it written very nicely because it's, and I should just follow how I say it written. Along the intersection, okay, x squared plus y squared equals 50. Okay, so in other words, along that green intersection there between the sphere and the cone, those points, hold on here. Let me just, these points here, all these points, the coordinates, their x and y coordinates have to obey this equation, x squared plus y squared equals 50. Okay? So what would the vector equation be of the two parameters? The vector equation of the two parameters would be r of xy equals, we let x be x, y be y, but z would be the square root of 100 minus x squared minus y squared. Okay, and that actually makes sense. That actually makes sense. Okay, because just one moment here. If we look above here on the surface, the sphere, the points on the sphere were x squared. One moment, Lexi, I'll get to your question. X squared plus y squared plus z squared equals 100. So that means z squared is 100 minus x squared minus y squared. And so this, we can represent this sphere here, okay, our surface sphere, as the square root of 100 minus x squared minus y squared. That's the z coordinate of, that's the sphere can be equivalently written as z equals the square root of 100 minus x squared minus y squared. So this vector r that's scratching out that surface S on the sphere, okay, if we let x be x and y be y, then z is going to have to be the square root of 100 minus x squared minus y squared. But the restriction on the parameters x and y is that x squared plus y squared would have to be less than or equal to 50. Okay, because on the intersection of the sphere and the cone, those coordinates on the intersection, the parameters x and y have to obey x squared plus y squared equals 50. But inside then, okay, inside the rim, which would be the the points that are inside on the sphere, those coordinates, those points, that the parameters x and y, that would obey x squared plus y squared is less than or equal to 50, because x squared plus y squared equals 50 gives you the rim, okay, and as you go inward, then x squared plus y squared is less than or equal to 50. Now let me see, there was a question here. Please let me know if you have any questions. The surface above, Lexi, is the surface above, okay, this surface S, okay, it's true, the surface rises above the boundary, but it's the z coordinates would increase. The z coordinates would be greater than the square root of 50, because along the boundary, the z coordinates along that boundary, that intersection, would all have square root of 50, because 100 minus, because 100 minus x squared minus y squared is the same as 100 minus x squared plus y squared. And that is 100 minus 50, okay, which equals 50. And that's along, and that's where and so you get the square root of 50, I should say, for the z coordinates along the intersection, because of this intersection. Okay, so what's happening though is you move inward on the surface, then the z coordinates get greater than the square root of 50, but the x and y values, x squared plus y squared, would be less than or equal to 50. Lexi, does that make sense? Does that help you feel comfortable? So let me ask you, when x and y equals 0, okay, when x and y equals 0, the like at the very top of the sphere, right here, okay, what's z equal to there? Well, at the very top of the sphere, x would be 0, y would be 0, so z would be just the square root of 100 or 10. Hey, that's the radius, right? That's the radius. So all right, let's go ahead and I want to say this the right way. Sorry, one moment here. I'm thinking about this a little more myself. I'm thinking about this a little more myself on this. One moment. Yeah, that's right. That's right. That's right. That's right. Because the red vector grows, it grows in length as it traces out different parts of the surface. It changes. Right. Let's see. Alberto says, how did you get the z coordinate that's circled in blue? Let me see here. You mean at the top? At the, oh, here. Oh, right. The reason that is because the surface S is part of the sphere. Okay, the shaded surface S is part of the sphere. So the spherical equation is x squared plus y squared plus z squared equals 100. That's the spherical equation. That's the equation of the sphere. So therefore, for any point on the sphere, z will equal the square root of 100 the z will equal the square root of the quantity 100 minus x squared minus y squared. So when we're finding the vector function of two parameters to trace out the sphere, the z part here has to be 100 minus the square root of the quantity 100 minus x squared minus y squared. X and y are free. Those are your parameters. But the reason we had to find the intersection, that we had to find the intersection here, this intersection, we had to find the intersection. I don't know why this is crazy. Hold on here. Hold on one moment. The pen sometimes it acts on its own accord. I don't know why. Okay, the reason we had to find the intersection between the sphere and the cone is so we could get a restriction on our parameters u and v, and we found that that x squared plus y squared would be at most 50. That's where the cone intersects the sphere. But then as you go inward on the surface, x squared plus y squared, hold on, let me just keep that button off. X squared plus y squared, I don't know why, hold on. X squared plus y, hold on. All right, one moment. One moment. Okay, as you go inward on the sphere, x squared plus y squared would be less than 50. Okay, and so now what you have, hold on, I'm going to go back here. Now what you have is you have your answer. You have your answer. One moment here. This is the parameterization for our surface if we're going to use the parameters x and y. But there's another approach to this. There's another approach to this. We don't have to use the parameters x and y. We can use parameters theta and phi. We could. It's convenient because we're our surface is a portion of the sphere. So if we go and look at this second approach, and you want to take good notes on this, the second approach here, I'm just going to I'm gonna parameterize this surface using the vector function of phi and theta. Phi and theta. Well, okay, that comes from spherical coordinates. So spherical coordinates, okay, well, we know that the sphere has radius 10. We know that the sphere has radius 10, so rho equals 10. But then I just, use the definitions from section 9.7 for x, y, and z. And that's fine. I have the parameterization of the sphere, but it's not correct unless I say what the restrictions are on the parameters. Well, it turns out that the parameters theta can go between 0 and 2 pi, and phi can go from 0 to pi over 4. That's the restriction on your parameters. Now the question is, why is that? Particularly, I don't think it's too hard for you to understand that theta, because a sphere is a bunch of circles connected together, okay? But of course the circles have different, you move them up. The theta has to go from 0 to 2 pi, right? But phi goes from 0 to pi over 4. And why is that? Well, what we're going to do is to see the restrictions on phi, here's the justification. So what restricts phi? It's the cone, because the sphere goes downward until it hits the cone. Where it hits the cone is where that sphere stops. The surface we're interested in, that part of the sphere ends where it hits the cone. So if we put in our parametric equations in the equation of the cone, we can figure out what the restrictions are on phi. So z is rho times cosine of phi, and x and y are as you see here. Okay, let me give you a moment to catch up. Let me know if you have any questions. Lexi and Alberto, you're feeling a little better? A little more comfortable? Okay, good, good. Okay, so yes, we'll see. Some people prefer using the parameters x and y, which are from rectangular coordinates. Other people prefer using parameters theta and phi, which are from spherical coordinates. In your exercises from 10.5, you'll need to be able to do both. And on your exam, for instance, you'll need to be able to do both. But we're trying here to find our restriction on phi, and I do a little algebra here. We have a common factor under this square root of rho squared sine squared phi. It's a common factor, and I factor it out. And then cosine squared plus sine squared theta is 1. So we end up getting rho cosine phi equals rho sine phi. Okay, but if you have rho cosine phi equals rho sine phi, you can divide both sides by cosine of phi. So long as phi is not equal to 90 degrees, and it's not in this case. You know, I'll note here, phi is not going to equal pi over 2. And this is going to give you then, this is going to give you 1, actually, and then the rows simplify out. So I'll tell you what, I'll divide by rho cosine phi. And so I'm going to get 1 equals tangent of phi. And so phi is pi over 4. And so see in the picture here, if you look here, right, I want to be careful not to, you know, there's the vector function. Hold on here, we can make this look good. You know, here's the vector function r. Okay. In this case, I'll actually maybe try to write this kind of tiny here. Not tiny, but, oh, that's too tiny. Hold on. Just a little less font. Yeah. This would be r of, well, in this case, theta is pi over 2, and phi is pi over 4. Okay. For, you know, that vector there. And the the vector function, or the vector, since it's a function of theta and phi, as theta and phi change, that vector moves around, and it scratches out that surface, that surface you see. And I've drawn, like, okay, well, for instance, here, one moment. Here, right here, that's why I kind of like to use 3-point. It shows just a little better. Okay, here. There, phi equals 0. Okay. And then here, phi equals pi over 8. Okay, because remember how phi is measured. So the point is, that would work also. That would work also. Okay, so you know, are there any questions? Are you on this, on how this works? Yeah, but you're okay. All right. How many like using the so remember what we have here. Remember what we have. We have two ways to parameterize this surface. The second way was using parameters theta and phi. And then these here were our restrictions on the parameters that forms the domain for the parameter space. That was the second approach. The first approach was to let x and y be parameters. And that gave us then, hold on, that gave us this vector function, and the restriction on the parameters is x squared plus y squared is less than or equal to 50. So this example, if you maybe obviously the recording the lecture, and it'll be available for you to watch later, but it's a nice example to really help you with this. Okay, are there any questions at all before I stop the recording? Give me a thumbs up if you're feeling okay, reasonable. You're feeling reasonable. Okay. Yeva's good. Angela's good. Logan's good. Noreen is sort of good. Mary's okay. Mary's good. Lexi's good. Matthew's good. Alberto, wonderful, wonderful. Arian's good. Okay, I'll stop the recording. We're done now with section 10.5.